Oh, hi. Hi. Oh, Professor, I haven't replied to your email, but yeah, that's good.
People didn't know the time.
Huh?
People don't know the time.
Well, some people are on Zoom, so I'll see.
I don't think so. Sorry, I'll have to leave 5 o'clock.
No worry, no worry. Yeah.
Start.
Yeah. Let's wait 1 minute. Can online audience hear us very clearly? Just double check. Great, thanks. Okay, welcome everyone. We are very honored to have a Professor Sam visiting us. And actually, I was just informed last week that he has a plan to stay visiting Boston for the Chinese New Year, and so we are very happy just to quickly arrange a seminar for him to speak. He will be speaking about quantum algebra of Chern-Simons matrix model and large and limit, and he's visiting from Shanghai Institute of Math and Interdisciplinary Science. That's let me remind the audience, please feel free to ask questions and interact with Professor Sam during the talk. Let's welcome Professor Hu. Please. Thank you.
Thanks, thanks to thanks. So for the organizer to have this seminar, I'm very honored to speak on recent work on quantum algebra of Chern-Simons matrix model and large limit. So this is a joint work with SIMIS and we also have So the first, I want to give some motivations of our work. So the talk will be consist of 3 parts. So the middle part will be first I give some motivation. So first motivation is about modify the concept of space. So we propose that the right concept of space.
So maybe speak a bit louder. Yeah, I need your microphone. So yeah, I hope so. Okay. Yeah, speak a bit louder.
Yeah. So we propose that the space, the concept of the space, needed to be modified for the use of quantum field theory, string theory, and we propose the modification to be an infinity algebra of space, and that is a joint work with also several other. And the second part is the title is on the title about the Chern-Simons matrix and its large limit. So then I will explain some consequence of this work, some consequence to understand holography in terms of quantum dual. So that is the motivation of the work. So first I want to explain that there are many problems with our current concept of space in terms of continuum. So this concept has a lot of problems. When people do quantum field theory, so you are doing quantum field theory over space. If the space is a continuum, then we know there are a lot of problems. So one of the problems is about path integral. Actually, path integral rarely exist as integration over this infinite dimensional space. So there is rigorous proof that this integral does not exist. So the problem of of this concept needed to be modified. So usually we modify to introduce some kind of cutoff so that the space, the resolution of space is finite, and so we need a cutoff. So there are several approach of cutoffs. So one approach is by lattice, or you can do a cutoff in the momentum space. Actually, you want to construct a theory over the space of cutoff. So that is effective theory based on this finite resolution of space. This is actually the theory what physics needed. So they need an effective theory over a cutoff space. So mathematically, we needed to understand this modification of space. So there's another way, two ways to describe a space. One is in terms of points. Another one is in terms of functions. So the function over space. So this is a ring. And if you, people consider this as a structure shift. So if you can use this to characterize the space. So then if you use this, then the prime ideas would correspond to figures and the maximum ideas correspond to points. So this concept would be larger than our space of continuum because there are some rings, there's no maximum ideas, but still you can consider as a space. Actually, for the field theory, the right concept of space should be functions not over a regular space, but over a superspace. So if you consider function over superspace, so the most interesting examples will be the deformed differential. So this is a differentially graded algebra. So this with this as describing a space, you have a lot of advantages. You can easily write down actions for all kinds of actions. So based on this. So there would be problems if you introduce a cutoff. The ordinary problem is like this. If you consider cutoff, then you consider the rings of functions, the multiplication of the functions. So when you do a cutoff, you have a projection. So the projection, when you do the projection, you often lose associativity. So that means this algebra is not associative.
You're thinking of something like momentum.
Momentum cutoff. Also, yeah, even there are several kind of examples. You can do like decomposition of by eigenfunctions of Laplacian. Yes. So
but lattice cutoff.
Lattice function itself is associative, but the cochains is not associative. Yes. So we are coming to that. That is a very good example. Yes. So then very basic problem is what is the algebraic structure of the regular space of functions of deformed differential. So we for this we propose that the right concept should be infinity algebra or module of infinity algebra. So we propose this is the concept of space for more general setting. So this way, infinity will restore associativity by homotopy. So why we have infinity? Because we need to have a homotopy. So let me explain several examples. So the first example is a lattice. So if you consider functions, algebra function over lattice, it is true. It is still a commutative associative algebra as the functions. However, if you consider cochains, so that is the corresponding concept of the deformed differential. So there's a theorem. There's no supercommutative associative algebra structure in the space of cochains. So this was a problem proposed by Komarov in the 50s. And so this way you need to have infinity. So if you consider lattice, you consider space of cochains. You want to restore this associativity, you need to introduce a homotopy.
So here you're thinking of cochains, well, you mentioned with deformed, but
Yes.
Simply show complex.
Right. So you need to have this infinity. There are several constructions. So first, by Whitney, we construct one product, and then people consider higher product to restore this associativity. The one-dimensional was constructed by Alexei Menev. And so we need a construction not only one dimension, but also for higher dimension as well. So you see, this is example is very important because when you construct lattice gauge theory, you need to have this structure. People has not realized that to use this structure. Another example is by Costello, that when he construct this topological strings BCOV theory and also this perturbative Yang-Mills theory. So you need to have another regularization. So he used this exponential decay of a Laplacian operator. So you insert this operator. So then you have some kind of regularization. This way, people can construct multiplication and by 2 and also higher multiplications. This is actually an infinity structure behind this. Then using this, it is able to construct. This is one of the key constructions in the topological strings, BCOV theory. So what I will discuss today is another example, that is non-common space. So this non-common space appear very naturally in the Chern-Simons matrix model. So here is the action of the Chern-Simons matrix model. You see there are some basic field Z, the gauge field, and S0 is the gauge field component corresponding to time, and lambda is the matter field, the fermions. So we can write down the action for the Chern-Simons. So you have this Chern-Simons action, and also you have this fermionic action. So this is the most important property for the Chern-Simons action is the gauging rise. So for this gauge field, when you do conjugation, it is still invariant because you take the trace. You take a trace. If you take a trace, then the conjugation will not be changed. Change the trace. And then you can consider this Chern-Simons action, the equation of motion with respect to A0. So this is people call a Gaussian constraint or the moment map, moment condition. So here if you consider Z, So people are the first to propose this model by Susskind. And the Z is an infinite matrix. And he want to construct a non-commutative Chern-Simons theory using this action. So soon that was constructed in 2001. So several months later, people consider the cutoff. So not to consider infinite matrix, but a finite matrix. But if you consider a finite matrix, then you consider this equation, variational equation. And if there's no lambda, there will be no solutions for this equation, for finite matrix. So this way, this is called anomaly. So this way, people are forced to add a new field, this lambda field. So that is matter field. So this matter field coupled with Chern-Simons. And then you have, this is actually Chern-Simons matrix model with matters. So that is the full action for Chern-Simons. So we will consider this, construct this and take a larger limit. So this way we construct a non-commutative Chern-Simons theory. So that is also one of the consequences of
Sorry, back to this map. You said Z is a matrix
yes.
and A is a SUN.
Yes, A is also a, so A zero corresponding to the time component. Yes,
What about the lambda?
a lambda is a vector. Yeah, so it's a matrix acting on vector.
So which part is the matter? Lambda is the matter.
Lambda is a vector.
What is the meaning of Z?
Z is a Kitty field.
Z is the key.
The Kitty field.
And what about A?
A is so you have zero component. Yeah. So this theory is 2 + 1 dimension.
Oh, I see. Okay.
Yeah, you have time component.
Z
Yes.
is Z and A together are.
Yes. Yeah. Okay. Okay. So if you take the time derivative plus x0, so that is correct.
Oh, sorry, just one more. What is Z plus?
That's a diagonal.
Sorry?
Bigger.
Diagonal.
Okay.
Yes.
Plus.
Okay.
Sorry, I have a question.
Yeah.
Where's the Lagrange multiplier here when you give the action?
Okay.
Yeah, where is that? Which one is it? Is it the lambda is the Lagrange multiplier in your action?
No, lambda is the matter field.
Okay.
Matter field.
Because because when we get the Chern-Simons action, then the Lagrange multiplier acts as a time
Yes.
portion. So is it A naught is the Lagrange multiplier?
Okay. In some sense, yeah, that's true.
Yes.
Yes.
Okay. And B here is just the magnetic field.
Yes.
And theta is that the theta term for Chern-Simons.
Yes.
Okay, thank you.
Yeah. Right. Theta is the correspond to the strength of a magnetic field. Yes.
Thank you.
Yeah. Okay. Okay. So that is the action.
Actually,
Yeah.
earlier you mentioned
Yes.
some way of thinking about anomalies, cancellation by adding matter fields, but
Yeah.
which kind of anomalies are we thinking right now?
The anomaly, so here, if you don't add lambda, and you consider this is as a finite matrix, there's no solution. Because you take a trace, this is 0, and you take a trace, here is non-zero. Yeah, if you consider infinite matrix, there's no anomaly. But if you truncate it to a finite matrix, that is anomaly. So that means you have to introduce a new field. Actually, with a new field, you give an edge state.
So here we have described 3D.
2 + 1. 2 + 1. Yes. But this 2 dimension is a non-commutative plane. A non-commutative. Okay. So now we would consider this Chern-Simons theory as a 2D 2+1, and this 2D is a non-common space. It's a non-common manifold. So non-common manifold. So what is non-common manifold?
But let's just double check. The lambda, the matter field, it also lives in 3D.
Yes.
Okay.
Yes. So depend on no, lambda only depend on T. Not depend on Z. So this is independent.
But does he have a space coordinate independence? The lambda?
Well, it's really kind of mysterious. So this is only as a quantum system. This is only one-dimensional system because you have integrate the matrix part. That's only time.
Okay.
Yeah. So that's the one of the interesting thing from this one-dimensional quantum mechanics system. We can reconstruct a space, non-common space. So space will appear when we do quantization and taking larger unit.
Sorry, I'm very another question. I'm a bit puzzled by the gauge invariant. Gauge transformation, U is the gauge transformation.
Yes.
So, but then this is the potential. So should there be another term, something like minus du?
No. We have this Chern-Simons, and then we have this Lagrange multiplier. So this we have this harmonic term. Harmonic term means to confine the particle into a disk.
Yes.
Yeah, random matter field. Okay. So then what is a non-common space? A non-common space is we should consider as the algebra of operators. And together with the Dirac differential. So that is a non-common space. So it's like you have some kind of non-commutative Dirac complex. So usually when we consider space, we consider this space responding described by a Dirac complex. So if you allow the structure shift to be non-commutative, so then you have non-commutative Dirac complex. So that's essentially what we mean by a non-commutative space. So here is a realization of a non-commutative plane. So we have these operators. We have these operators. It's like a Heisenberg algebra. And we have also the Hilbert space of boson. So using this, you have these operators and the Hilbert space. Now we need to construct a Dirac complex. So we have this complex. You have operators times the formula. But you need to construct a Dirac exterior derivative, a Dirac differential. So in the case of infinite matrix, you can construct this Dirac differential. So that is just a commutative. Yeah, so that's easy to verify.
What is that little?
Little a is a is a variable. So that means for any operator, you do conjugation by Q. So Q is the operator. Yeah, we want this to be a Dirac complex, a Dirac differential. So for any operator, you just do a conjugation. Yes. So that is the distribution of a non-commutative plane. So basically, we consider this as a Dirac complex. But if you consider a projection, because this non-commutative plane is too big, we want to have kind of a non-commutative disk. So then you project this Hilbert space into a finite dimensional space. So you only consider some finite space. So you have inclusion and projection. You have two operators, inclusion operator and projection operator. So then this Z operator can also be projected into this finite dimensional space as an operator of finite dimensional space. So you can start a similar drum complex, drum derivative. However, if you compute the square of this drum, so that's not zero. So this means if you do a projection, so the space itself, you have a kind of a boundary. So you need to introduce some new operators to construct a drum complex.
So this predicted that we were actually think of as quite hard.
Yes. Yeah. So this is what we modify. So you need to have an inclusion and also projection. So if you have this operator, that's corresponding to this lambda. So you have this operator. So then you calculate the square of this operator. So we found the square is belong to the center. That means if you do belong to the center and to the conjugation, that's zero. If it belong to center, if only the Z satisfies this ideal HM equation. So this way we construct what we call the fuzzy disk. So that means we have this Hilbert space, a finite dimensional Hilbert space, and have this inclusion and projection operators. And then we can construct this drum differential. So the drum differential, the square of this is equal to zero, as long as the Z satisfies the ABHM equation. Or in this case is this Gaussian constant equation. For 4 dimension is the ABHM. For the 2 dimension is the Gaussian equation. So this way we construct non-commutative disk. So then the Chern-Simons theory matrix model can be considered as a gauge theory over this disk non-commutative disk. So we give this geometrical interpretation of Chern-Simons matrix model. So now, so next we will consider how to do quantization. So to quantization, there are 2 ways, at least 2 ways of quantization. So one is called a canonical quantization, another is called a geometric quantization, and both are very interesting. So in this today's talk, I only consider canonical quantization. However, we also did geometric quantization. So that uses a lot of algebraic geometry, and in some sense, that's to the quantization that's easier than canonical quantization. But canonical quantization is down to the earth, so it's especially easier to be understood by physicists. Okay, so to this canonical quantization, we consider all the Z's, the component. This is a matrix, and each matrix component can be considered as an operator. So we have this set of commutation relations. So this gauge field and the lambda field. So that is the canonical quantization. We have the Fock space. However, the Hilbert space consists of physical states. This physical state has to be constrained by Gaussian constraint. So this moment map condition applied to physical state has to be zero. Actually, this is the condition so that the physical state is invariant and the UN condition. So in some sense, so the physical states are the states respect to the gauge symmetry of UN gauge symmetry. So that is the meaning of this condition. So using this condition, we can construct all kind of physical state. So if you consider the U1 part, this condition will be like this. So that is simply if you add from the ground state and you add a lot of lambdas, creation operators. So this condition means the number of lambdas equal to kn. So that is condition of U1 condition.
So we get that equation for any physical state?
Yes, any physical state has to be obeyed this equation. So that is the U1 part of this UN symmetry. And then if you consider the full UN symmetry, SUN symmetry, so this the physical state should be SUN tensors, UN tensors. So here I write down the physical one of the physical state, the typical physical state. So you have lambdas and have these. So this one you apply to the ground state. And then, so all these are commuted. All these are orbital commuted. A lambda, which is vector, Z is a matrix. So then you consider I1 component and I2 component, IN component. So you use this tensor to contract. So this gives you a singlet of SUN vector. So that is the SUN tensor. So that is the gives basically physical state. Actually, these states will be the formal basis of the Hilbert space. And then you consider operators. This we call the phonons. You can use the phonons to act on these states. So that's give you more states. So that is the general structure of a physical state. I will describe this into diagrams. That's might be easier to understand. But that's for later part. So first I consider the quantization as algebra. So then as the Hilbert space. So this way you can construct the ground state. So to construct ground state, you simply calculate the energy, and you construct the lowest energy. That's ground state. And the lowest energy is so the z's. You have lambda and z's, and the number of power of this will be. So they cannot be the same. The index, if they the same, that this anti-symmetric tensor would be zero actually. So all this, the power of these are different. So then the lowest ones would be from 0, 1 to n-1. So that corresponds to the ground state. Actually, this ground state corresponds to the Loftin's wave function. We can not only construct the gauge group, internal gauge group, not only for rank 1, we can also consider rank higher rank. For the higher rank, the ground state will be more complicated. So actually, they are corresponding to a Young diagram of SUT. So this can be easily to be understood when we draw diagrams. Okay, so now we consider the operators. What are the operators? Gauging random operators for Chern-Simons matrix model. So here we have two gauging random operators. So you can do this Z and Z diagram with this power and do a synchronization. And then you can apply this lambda field. So this is the gauge invariant orbit. If you apply gauge transformation, that is in. This orbiter more or less like Wilson loop operators for the continuum space. But we also have another operators that we call the formals. So you consider the Z and the Z diagram and raise the power and do symmetrization and take a trace. So this is clearly a gauge invariant operator. Actually, these operators are the generators of affine Youngins. So affine Youngin naturally appeared in this construction. So we have two sets of gauge invariant operators. So very concretely from matrix model. And so the important thing is to calculate OPE of these operators. This gauge invariant operator. And so this is actually the interesting stuff in our work. So this work was originated by David Gatto. So he calculated the commutative relations of these gauge invariant operators.
So,
So E. So here, yes. So here we have matrix, and then you have the two vectors. Yes. So we call this loop operators. Because when you consider a vector, you have some localization to a point. So it was David Gatto. He tried to calculate the commutative relations. Actually, he did this by using computer to calculate. He guessed conjecture formula for the commutative relations of E operators and also for the T operators. So this was what he conjectured 2 years ago. And this commutative relations is very important for us to take a larger limit. So we will explain why it's crucial to have this commutative relations. So if you see the commutative relations, you will see that so there are some extra terms of quadratic term. So beside this, the neural terms, there are quadratic terms. So we'll see these quadratic terms will disappear when we take a larger limit, because we need to take a rescaling of this operator. So there are two properties of this operator. So the first, this operator does not depend on capital N, the size of the matrix. So this is independent of N. Commutative relations of E and T. And the second, so you have this quadratic operators. But the quadratic operators, the sum of the index is smaller than the previous index. So when we do so we will see when we do rescaling, this quadratic terms will disappear. So this is what we did. So when we have this commutative relations, and you calculate you can calculate. So this is the cosmology algebra component. And then you calculate the commutative relations. So we have a degree. The degree is called m plus n. So then we found that the commutative relations, we use the previous commutative relations. So we will have the highest degree and the lower degree. So this degree corresponds to the rescaling. So when you have the rescaling terms, take a larger limit, this lower term will disappear. So this is the technical part. So we have to rescale this operator, this cosmology, the component of the cosmology algebra. So for each n, so we rescale by capital N, and the square root of the capital N times. And so similarly, we put the rescaling for the phonemes operator. So using this commutative relations of the conjecture by David Beato, then we can show we're taking larger limit. So this gives a cosmology algebra. Yeah. So this is the part. This is the part we have as an algebra. It can reproduce cosmology algebra. Actually, not only cosmology algebra, but also this affine Young. So if you consider this T operators, you form the algebra of the Young. So so we have seen the taking larger limit. The key is to have this commutative relations. And so we have 3 proofs of this commutative relations. So first, we did it by hand. So just cut this component. So we have several months calculation to really prove. So later, there are some better method. One is by generative function. So that is appeared in the paper using generative. There's another proof by using this what we call a categorical relative. So when you do geometric computation, you can diagonalize one of these first. And then the other z diagonal, you have a special form. So this we call the categorical relative. So using categorical relative, you can prove this commutative relations. That's easier than using this canonical. So basically, we have 3 proofs for this conjecture. Yeah. Okay, so that gives the first part. So as an algebra, we can take the larger limit, and we can reproduce cosmology algebra. Actually, we get more. We actually have this affine Young algebra. This affine Young algebra is kind of important to understand the invariability structure of the system. So that connected us with the universal system. So the next, we consider this Hilbert space. So the Hilbert space so these are all the physical states obeyed by constraint by Gaussian constraint. So we can construct basis of the Hilbert space. So using this Phonemes operator acting on the ground state. So that gives the basis of the Hilbert space. Then using this basis, you can construct 2 operators. So one is creation operators. Another one is annihilation orbit. Actually, these orbits are very similar to Nakajima's orbit on the coherent shift. So that's a 4-dimensional. So there's similar orbit construction as Nakajima. So you have this creation orbit and annihilation orbit. So then we need to consider the problem of taking larger limit of the Hilbert space. So this is the this is like to have the representation of this Hilbert space. Here's the representation. So we have proved that this T operator over where we take a larger limit asymptotically it's like this. So then if you scale by the square root of m plus n times, and this the remaining part will disappear. You only have this one. So that depends on m and n. So if m, so m is correspond to the z power, and n is the z diagonal power. So if m is less than n, you have more diagonal than the annihilation operator. So this, when you take a larger limit, you automatically come to n minus n operator. So the operator only becomes n minus n. So this is kind of interesting. Because originally we have 2 parameters, but you take a larger limit. The operator is like a Nakajima operator, only have 1 index. That's only depending the difference of these 2 index. So similarly, if n and n, n is bigger than, but in that case, the operator will be annihilation operator. So this is the basic construction of the representation of the algebra. So the algebra, the representation will degenerate into this cosmology. Okay. Yes.
So in the more familiar internal motion theory, like we have a data like a gauge group and level, let's say S is the gauge group at level K.
Right.
And there's some final number of states, let's say on torus. And for example, T2 for torus times S1, and there's only, let's say S2 level K is a K plus 1 states on torus. Okay. And this is dimension of the space K plus 1. But here, there's some like some interference formula in certain manner, say how many states there are, how many states we are coming, and also input data. In the transform efficiency, the input is gauge group level. And here what the input data, what the number of states. Let's say put out some 3 numbers. I guess you're writing the matrix form, but I wonder whether there's something I can still kind of understand the structure of the space. Right. Based on this formula, which I can put in easily.
Yes, actually the Hilbert space is kind of subtle, because for each finite n, the Hilbert space is infinite. However, you have the energy, you have high energy, so but the low energy of this Hilbert space will be embedded into the limit of Hilbert space. So that kind of interesting that for each n, there will be some energy. So this low energy states will be embedded larger limit of the Hilbert space.
What is the energy?
Energy is so you can calculate them. So yeah, what is the energy? So energy means you calculate the number of diagrams,
Number of
creation operators. Creation.
but there's an energy operator.
Yes, the number of it.
Just the number of it is topological. There's no real.
Right. But if you do cut off, like a Chern-Simons itself is topological. But when you do correlation, you produce a cutoff, a metric. So that way you have this. Okay. So taking a larger limit, we have this Hilbert space representation.
By the way, the mean in topological here means that space-time metric independent here. Is that what do you say is topological?
Topological means we don't need to introduce a metric like for the Chern-Simons action. But however, like if you do a correlation, you take a cutoff. That's right. So that means you already introduce something.
Yes. Yeah. So it's not quite topological.
Right.
Yeah. I mean, just even if you go to some because if you want to integrate the field space, it's having the major, you have to have some regularization. It's actually not quite topological. Right. So here, similar.
Right. So this way we prove that you can really take a large limit. So if you take a large limit, that means you, as a consequence, that means you can construct a Chern-Simons theory, non-commutation. So then that depends on what kind of Chern-Simons, what kind of space the Chern-Simons theory will have. So depending on the parameters you choose, n and c. So if n and theta times n and theta is finite, like n goes to infinity, and theta goes to 0, but the product is finite, so that will be a disk. But if you fix theta, that n goes to infinity, you have non-common plane. So that gives Chern-Simons theory over non-common plane. Yeah. So depending on how you choose parameters, you have a disk, and you have a plane. So there will be some consequence of this construction. So once is affine Young so we have this T orbital, the component of T orbitals are the component of affine Young. So we here have this orbital algebra obeyed by this Young. But we also have the representations of the cosmology algebra. And then we can also construct a non-common plane and a non-common disk. So this disk we call fuzzy disk. So you have, take a larger limit, you really have a Chern-Simons field theory over non-common plane or over non-common disk. And so what do we propose? That what we are going to do. Actually, we have not finished. That so the next step is will give us the holograph. So you have the non-common plane, and this non-common plane is a kind of a space constructed from this larger limit. So the space appeared in taking larger limit. So we did some technical works, but now we want to understand what would be the consequence of this work. So one thing is that we can construct a space out of a quantum mechanical system. You really have a non-commutative disk. You have a disk, you have a plane. But with conjecture, we also have annulus and also a disk with multiple holes out of this construction. So then it'd be interesting to show that a conformal field theory will be reproduced by this taking line. Actually, I think we have already got this conformal field theory. If you take a larger limit, you have ground state will become a lawful function for some special case. And the lawful function are the correlation functions of the conformal field theory. So the interesting things perhaps will be also the correspondence of AS3 and the CFT2 that correspond to two boundaries of the space. So that's something we need to work. And the CFT will have a factor of 2 gauge groups. So to fully understand this work, I think we need to consider the proposal by Costello and Lee. We call the Costello-Lee duality to understand the holography. So this proposal was proposed by Costello and Lee in 2017, this paper. So that is what I copied from the paper. So what's the meaning of so if you consider difference type 2A and type 2B, and also consider difference in problem 3 in a brain answer. So the difference, we can consider difference as a defect in string theory or in superbundle. So then you can consider 2 things. So one is the algebra of operators of the supersymmetric game theory leading on the difference. And then you take a limit, larger limit. So this corresponds to the field theory, the part of field theory. And then you can also consider the algebra of operators in perturbative twisted superpolarity on the location of a defect by the start of difference. So then what they propose is that these 2 algebras are co-good. I think perhaps this is the first formulation how to understand the holography mathematics in terms of the So one is this algebra of operators of field theory. Another one is the algebra of operators, the deformations of the superbody. So those 2 should be co-good. So that is the proposal. And perhaps our case will be a special case of this. Because in our Chern-Simons matrix model, we consider this as an improvement. Actually, as the algebra, they are co-good with 2 algebra. So there are some elementary examples of the probability. And also in writing algebra of space or Schwabe-Einberg algebra as a big set. So if you do deformation, we are really good. Yes, elementary example. But in our case, so we have with Costello dual. One is coming from Chern-Simons theory. From Chern-Simons theory, as we mentioned, we have this affine unit. So this actually appear naturally from this Chern-Simons matrix. And we also have this universal invariant of the structure shift of the plane. And so deformation of this invariant algebra will be Costello for affine units in this case. So I think for the holomorphic Chern-Simons, this was done by Costello using this PV deformation. In our case, it's like a two-dimensional case. Two-dimensional case is like Keller Chern-Simons. It's also Chern-Simons coupled to ECOVC. And in this case, it's a Keller Chern-Simons rather than holomorphic. So then we have this algebraic equivalence of 5 unions in the W algebra. So that's what we did before by Mali. And combining all this together, we will have this dual of 5 unions and the universal invariant. So this. Okay. So this shows these are the consequences of matrix projection. If only after you take in larger limit, so you can consider this problem and you can show you are very good. So that is okay. So that is the part I want to say. Yeah, exactly. Thank you very much.
Thank you. Yes. Any question from audience and online audience? Feel free. Yes, okay. So, okay, in Chern-Simons theory, the usual one, we consider Chern-Simons theory on free manifold. And in your case, we say we have two of the space dimensions, somehow non-completed. Right. And there is some relation to the matrix model discussed today. And is there a generalization in this world? Or we consider maybe even dimensional space of more than 2 dimensions, whole states.
Yeah.
So we can also consider multiple non-completed coordinates.
Right.
So this happens for other dimensional space plus time. Space is even. So there could be something like that.
Yes.
So are we also with the structures we could expect for this case?
Yes.
Was not.
So there are parallel theory for 5 dimensions. Yes. This was correspond to high dimension polygon.
On the protocol side, though, but the matrix model really I'm not familiar with. So you think there is also a similar procedure?
Yes. Yes. Yeah. So this could talk to N5 group. So here, so today's talk is about the N2 group.
So any other comments on the audience? Yeah, not okay. We should think.
Okay.
So
Yeah, thank you very much.